Today we will start with the new topic within the same chapter, systems. So what is a system? A system is nothing but a mathematical model, okay, of a physical process that relates the input signal to the output signal. Okay. So what it says is that if we try to relate the output from a system and the input from a system, then there exists a mathematical model given by y equals to tx, where tx is the transfer function. Okay, where t is the transfer function of the system. This transfer function of the system is nothing but a mathematical uh, model which helps us in transforming the input of the signal to the output of the signal. Okay. So what are the different types of systems? The systems can be as simple as single input, single output system, or multiple input, multiple output systems. There are many other types of the systems also, like multiple input, single output systems, but we will be uh, restricting ourselves to single input, single output system and multiple input, multiple output signal, just for the sake of the better understanding. Okay. No, now in the single input, single output system, say for example, we have an amplifier. Say for example, the amplifier is a non-inverting amplifier. So in a non-inverting amplifier, what is the input-output relationship? The output V0, it is given by 1 plus R2 by R1 multiplied by V in. What is the V in? V in is nothing but the X. V0, it is nothing but the Y, and this mathematical formula, this relationship 1 plus R2 by R1, sorry, this is R2 by R1, it is nothing but the transfer function of the system. So this is one of the simplest method to understand what we mean by system. So an non-inverting amplifier, it is a system because when we give an input to the system, there is a mathematical operator, or the mathematical formula is there when we where we modulate the input signal such that we get an output signal. Okay, this is how it goes. Now in this non-inverting amplifier, we have a single input V in, and we get a single output V0 or VO. Okay, so an non-inverting amplifier, hence it is a single input, single output system. Okay, now we may have systems where we may have different inputs which are given to the to a particular system. Okay, say for example, in biomedical industry we have a very common device known as multi-parameter monitoring system. As the name suggests, multi-parameter, that means it measures multiple parameters. So if it is measures and displays information about the multiple parameters, the input will also be different. Okay, multiple in nature. So what might be the inputs? The inputs may be the signals from the ECG amplifier, SpO2 amplifier, okay, BP measurement system, temperature system, thermistor, okay. So if you see in multiple input systems, we have n number of inputs. So it may be from the ECG sensor, it may be from the SpO2 sensor, it may be from the BP sensor, it may be from the temperature sensor. Now what should be the output? In the output from the ECG sensor, we may calculate the heart rate, SpO2 sensor, oxygen saturation, okay. BP, we may get the BP either systolic or diastolic, okay. Then temperature, we can get the body temperature. So in this kind of system, this multiple input multiple output system, we can see the system is able to handle multiple number of the inputs, and accordingly it can generate multiple number of outputs also. Another classical example is the ECG machine itself. If you look, if you go to any clinics or hospital, and if you go for this ECG measurement, you must have seen that during the ECG recording, we use multiple electrodes on our body. Okay. And in the output, we get several curves. Say lead 1 curve, lead 2, and so on. And so on. So there are various lead signals. So here also you can see there are multiple electrodes. So from these multiple electrodes we are getting multiple input, and from the output also we are getting multiple outputs. The same is the case with EEG signals. Over there also we can have multiple electrodes, and at the output we can get multiple output. Okay. However, if you look into the machines, the ECG machine, it appears as a single device or a single system, right? The EEG machine, it appears as a single system. So from here we can see that we can have different types of systems which may be useful in medical industry. Okay. Now the classification of the signals, the systems, sorry. So in the classification of the systems, we have several types of systems. The first one is the continuous time and discrete time systems. Second is the systems with memory and without memory. The systems without memory, they are also regarded as memoryless system. Okay. Then we have causal and non-causal systems. Then we have linear systems and non-linear systems. Then we have time invariant systems and time varying systems. Then we have a combination of the linear systems and time invariant systems. So the systems which follow both the linearity and the time invariance, they are regarded as linear time invariant systems. In short, we call these systems as LTI systems. Then we have stable systems, and then lastly the feedback systems. Okay. Now When we talk about the processing of the biomedical signals, we are mainly interested in the linear time invariant systems, okay, which are causal in nature. Okay, what do you mean by causal? Causal means that there is a cause. Okay, so causal linear time invariant systems. So if I give you in the exams that you find out whether a system is suitable for biomedical signal processing or not, then what you have to do, you have to check first the causality of the system, second you have to check the linearity of the system, and third you have to check the time invariance of the system. If the system is a causal system, it is a linear system,
Sir,
and it is a time invariant system. If it follows all these three, what do you call,
sir,
it is, just a minute.
sir,
Yeah. So if it follows all these three criteria, then this system can be used as systems for biomedical signal processing. Now coming to the first type of systems, continuous time and discrete time systems. In the continuous time system, the signal which is used as the input, it should be a continuous time signal. Subsequently, the continuous time system, it also give an output which is continuous time in nature. Okay, so continuous time systems, they have a they have inputs and outputs which are continuous time signals. Okay, then the next type of system is discrete time signals systems. So in the discrete time systems, the input and the output both are discrete time signals. Okay. Now let us take an example for the continuous time signal. One of the simplest example is the thermistor. Okay. Now in the thermistor, it is an analog sensor, right? And the output which is being generated by the thermistor, it is continuous time in nature. Now suppose the change in the voltage across the thermistor, whatever we are getting, if we record that, or if we process that using an analog circuit, say for example inverting amplifier. Inverting amplifier, so it takes the signal from here, and inverting amplifier, it converts the signals into an output signal yt, which is again continuous in nature. So this inverting amplifier or even the non-inverting amplifier, they are continuous time signals. Now discrete time signals, all the digital signals, they are discrete time signals, discrete time systems. Now are there any what do you call, sensors? Yes, all the digital sensors, all the digital sensors, they are discrete time signal generators. One of the common example is DHT 11, DHT 11. Even we can have DHT 22. These are digital sensors, and they are dual sensing sensor. That means it measures the relative humidity plus the temperature. Okay. However, the relative humidity, it is measured using a capacitive sensor, and for the temperature we have a thermistor. Okay, but you would say that both of these are continuous time sensors. Yeah, these are continuous time sensors, but post processing, after the measurement is being sensed by the capacitive sensor and the thermistor sensor, we have a analog to digital converter which are inbuilt within these DHT11 and DHT22 sensors, and they convert the analog signals or the continuous time signals into the discrete time signals. Okay, and then those discrete time signals, they are being processed using the microcontrollers or microprocessors, and in the output we again get the discrete time output. Okay, now systems with memory and memoryless systems. A system is said to be memoryless if the output at any time, it depends on only the input at that same time. Okay, so if you consider this first equation, yt equals to r of xt, so input at a particular time is generating an output at that particular instance. Okay, so if you consider this thing, this equation, that means at y0 we will be having r of x0. See the present instance, at the 0th time instance we are getting 0th, we are getting output at the 0th instance only. Similarly, if you go for y1, it will be r of x1. See the time instances both are same. Similarly, if you go on the negative half, y of minus 1 would be equal to r of x of minus 1, right? Same instance. So it is not dealing with any of the past inputs. So that means the output signal, they are not dependent on the past inputs or past outputs also. Okay, so while doing any work, if you are not considering your past activities, then you are said to have that you are not bringing any memory into your work. The same thing happens with these systems too. So any memoryless system, they are the system which do not take the past inputs and also the past outputs to calculate the present input, present output, sorry. Okay, so such systems, they are regarded as memoryless system. One of the classical example of the memoryless system is that any circuits which are made with resistors, any system which are made with resistors, they are regarded as memoryless system. Okay, so if you see any inverting amplifier, non-inverting amplifier, then differential amplifier, okay, you give the present input, you get the output at the present instance only. So these systems, they are any circuit which are made with this with the resistors, they are regarded as memoryless system. Any system which has capacitors or even the inductors, they are memory systems, and they consider the present input values also to give you the present to give you the present output. Okay. So coming to the causal and the non-causal systems, the causal systems, they are the one where you take the input, where your input or the output is dependent on the past inputs. Okay, if they are mm, if the if the output of a system is dependent only on the past input, then they are called causal system. So let me make a time scale. In a general scale, the time index 0, it is considered as present. Okay, anything from this present instance, on anything on the right hand side from this present instance, it is, these are future values, and on the left hand side they are the past values. Okay, now you consider this equation, y of t equals to x of t plus 1. So let us consider y of 0, then it would become, if we are considering t equals to 0, then our equation becomes y of 0 equals to x of 1, right? Now in this case, if you look, y of 0, we are at this present instance 0 index. However, we are taking value from the future instances, so this is a non-causal system. Okay, however, if this equation would have been yt equals to x of t minus 1, then what would have happened? Y of 0 equals to x of minus 1. So now my x1 input would have been on the left hand side. So this is a causal system. Then we will check some values in the positive side. Y1 equals to 1 minus 1, 0. So y would have been at 1. So x0 would have been on the left hand side. So again from here we get it is a causal thing. And next again, if we check the negative side, y of minus 1, it would be, it would what we would have got? We would have got x of minus 2. Again, this time index, it is on the left hand side of the output signal time index. So again it is causal. So in each of these time indices, at 0 time index, at positive time index, and at the negative time index, we found that the system is causal in nature. Hence this system, it is a causal system. It is a causal system. Then if you talk about yn equals to x of minus n, what you would have got? Y of 0 equals to x of 0. This is causal. Then y of 1 equals to x of minus 1. This says it is causal. Y of minus 1, it would become x of 1. Now here there is a problem, right? So this system since it is non-causal when the time indices are negative, even though it is a causal system at zeroth time instance and at positive time instances, this system is a non-causal system. Okay. Another important thing which needs to be kept in mind is that all memoryless systems are causal systems, because you will be having yn equals to, say, capital A of xn. So always the time indices will be the same, whether you go in the negative one, so it is say negative 1, then it will be a of x of negative 1. If you say y of 0, then it will be x of a multiplied by x of 0. If it is y of 1, it will be a of x of 1. So whatever is the time indice for which you want to calculate the output, it will take the input value at that time indice only. So hence these the memoryless signals, they are uh, causal systems. Okay, am I clear? So if you see over here, I have just explained these things, whatever I have just told you now. Then coming to the linear systems, in the linear systems, there are two important properties. The first one is the additivity property, and the second one is the homogeneity property. Okay. So any systems which follows the additivity rule and which follows the homogeneity rule, they are regarded as linear systems. And if any one of these do not follow this this additivity and the homogeneity rule, then they are called non-linear system. Okay, say for example, let us take the additivity rule. So consider a system where we are giving an input x1 to a system which is having a transfer function of t, and we are getting y. Take the example x and y. Sorry, x and y. So we have the input this thing. Now what it says is that suppose at a particular instance of time, say y1, my output was t of x1. Okay, that means I have given the input x1 and I have got the output y1, which is equals to t of x1. Similarly, at another instance, when I gave an input of x2, my output was y2. Okay, so this is condition 1, this is condition 2. Now the additivity rule says that if we give an input of x1 plus x2, then our output should be y1 plus y2. Okay, that means, say for example, in inverting amplifier, you are having a gain of 2. Say you are having a gain of 2. So initially you give an output of input of 1 volt, you get an output of 2 volt. Okay, and in the next stage you give another input of 2 volt, you get an output of 4 volt, right? So I am just taking the magnitude. Okay, I am talking about inverting amplifier. Okay, talking about the inverting amplifier. So we all know the gain is equal to -2. So I am just taking the modulus over here. Okay, just for the sake of understanding. Now, what if I give a 3 volt output wherein we are having this x1 of 1 volt and x2 of this thing. So we get 3 volt, we will be getting 6 volt as the output. Now, if we add up over here also, input is 3 volt, output is 6 volt. Okay. So this is matching, right? So when we have given an input of x1 plus x2, which is basically 3 volt, it should give the same output as that of the output of in the previous two instances what we have given. For this x1 we have got 2 volt, for the second instance x2 we have got 4 volt. So if we add up this value, whatever the value we should get, it should be equal to the input value x1 plus x2 when we give the that as the input. That should be the output of both the systems should be equal. Am I clear?
Yes, sir.
Yes, sir.
Okay. So this is the additivity rule. Now similarly, we have the homogeneity rule. What this homogeneity rule says, the homogeneity rule says that suppose you are giving alpha x as the input, so you get say your output would also would be given by alpha y. Okay, where this alpha is a scalar quantity, say 2, 3, whatever. So it is a scalar quantity. So if you give an input x which is being multiplied with alpha, then you should get y which is also multiplied by alpha. Let us take the case of this inverting amplifier itself. We will just take the magnitudes. So in that case, suppose I give you a 1 volt input. Okay, amplification we have talked that A is equal to 2. Now I multiply this with say another 2 volt. So what I should get initially when we were having x1, we were getting 4 volt. Sorry, for x1 1 volt, so we were getting 2 volt. Now when we are giving alpha x1, so it is 2 volt. So now what will be the say we call it as x1 dash. So what should be the output? Output is 2 multiplied by 2, 4 volt, right? So what is this? This is nothing by 2 multiplied by previous output, right? Y1. So herein in the homogeneity system, we first have to take this into account. With whatever scalar value we multiply the input, and the output also, that scalar value is getting multiplied with the output. Okay. Now at different time instances, we give two outputs, two inputs. Say at one instance we give alpha 1 x1 and the other instance I give alpha 2 x2. So I get a combined output of alpha 1 y1 plus alpha 2 y2. Okay. So if this follows this equation, then this equation it is called this thing what you call superimposition property. Homogeneity is we are having this scaling, okay, and then herein what we have done, we have taken both this additivity, a combination of the additivity and the homogeneity what you call properties, and combining this we have come with this superposition property. Okay. So in general, if a system, it follows additivity property and the homogeneity property, it also follows the superposition property, and the systems which follows the superposition property, they are linear systems. Okay. Now let us look into some examples. Say we have yt equals to t multiplied by xt. Okay. So x1 is equal to y1. Okay. So x1, when we give an input of x1, sorry, when we give an input of x1, we get y1, which is equal to 2 into x1. I'm not writing the t, okay, for the sake of convenience over here. In another instance, I give x2 as the input. I get output, which is equal output y2, which is equals to t multiplied by x2. Okay. Now y dash, it is equals to t. What is y dash? Y dash is nothing but y1 plus y2. Y1 plus y2. Okay. Now if you add these two, what you get? T becomes common, then x1 plus x2. Then next, in the next level, what you have to see is that y double dash, where the input xt is being changed with the fraction of x1 plus x2. Okay. So y double dash, we get the t over here, and then this xt, it is being changed with x1 plus x2. Okay. So if you see this c and d, they are equal. Okay. And this is nothing but your linear system. You can correlate this with the inverting amplifier example, which I said just few moments back. In one case, you are having the input 1 volt, you got 2 volt. When the input was 2 volt, you got 4 volt. When you say that I can add up these two values, this y1 plus y2, I checked 6 volt. So say this comes out to be 6 volt. In the next instance, what I did, I took a combination of x1 plus x2, which is basically the 3 volt, and then I passed that 3 volt into the system, which gave me again 6 volt. So this was the output from the second part of where I have given an input of x1 plus x2. Are you getting my point? So in both the cases, we can see that the output remains, that is in the case of our example, it is 6 volt, that remained the same. Hence this system yt equals to t multiplied by xt, it is a linear system. Okay. Similarly, we can go for another system whose transfer function input output relationship is given by yt equals to x squared t. Okay. So x1, for x1 we get y1 equals to x1 square, y2 it gets x2 square, y dash t, where outputs y1 plus y2 is calculated, it is basically x1 square plus x2 square. However, in y double dash t, uh, if you consider this as xt square basically, so our input is being changed, so our input is x1 plus x2 and to the power whole square. So if you see c and d, they are not equal, so this system, it is a non-linear system. On the contrary, if you just move the square from x square and put it to t square, so if you see yt equals to x of t square, now y1 equals to x1 t square, y2 equals to x2 t square, y dash it would be again x1 t square plus x2 t square, and this y double dash, this input is changed. This is the input, total input. Okay, input is x1 t square plus x2 t square. So this system becomes it is a linear system. However, the previous one where we are squaring the input, that is not a linear system. Okay. Similarly, over here, if you have a system given by yt equals to x of t plus 1, so we get x1 t plus 1, x2 t plus 1, and then addition of these two. And this is this one x1 t plus 1 plus x2 t plus 1, and y double dash, it is x1 t plus 1 plus x2 t plus 1. So this is a linear system. Now, time invariant system. A system is called time invariant if a time shift, that means delay or advance, in the input signal causes the same time shift in the output signal. Thus, for a continuous time system, the system is time invariant. That means it does not change its characteristics, time variance characteristics with time, if it follows this equation. That means if you change the input by an advance or delay an input by a particular time delay tau, the output will also be delayed by the same time fraction. Okay, this is also the case in the case of the discrete time systems. So let us take this example and let's see what I meant to say. So yt equals to t multiplied by x of t. So herein we give y t comma k, which is equals to t multiplied by x of t minus k. In this case, the time t is being delayed by a factor k. That means the signal is being delayed by a factor k, t minus k. Okay. In the next instance, whatever the t values we will be having, we will be replacing it with t minus k. In the first instance, what we did? In the first instance, we delayed the input signal. Okay, what is the condition over here? We are delaying the input signal. We are not touching the transfer function component. Okay, herein the signal component is xt, so we delayed the signal xt minus k. Okay, in the next instance, what we did is that wherever we will find t, we will replace it with t minus k. See, we are replacing it with t minus k. Now we got two equations. Now, are these two equations equal? No, because if you compare this fraction, the t fractions, it changes with time. So this system, it is a time variant system. Okay. Similarly, if we get another system yt equals to x of t plus 5 of ut, now we are delaying the input. So in the delaying of input, we get t minus k. The time period of this ut is not changed because this is not an input. It is not an input. Hence, it remains as it is. However, when we replace t with t minus k, this ut fraction, it also gets changed. Okay, so this is also a time variant system. Similarly, x of t square, it is a time variant system. On the contrary, x square t, if you see, it is a time invariant system. Okay. As I already told you, any system which is following the linearity and the time invariance characteristics, they are regarded as linear time invariant system. Stable systems means any systems, if you give a bounded input, that means you are having a system which is having a transfer function of t, if you give an bounded input, that means which is finite in nature, you should get an output y1 which is also finite in nature. Such systems, they are regarded as stable systems under the under this category: bounded input, bounded output, stable system. This is because if we give an input which is tending to infinity, this system will not be able to handle this signal, and your output will also be uh, infinite. Okay. Hence, while describing this the stability criteria for the practical purposes, we say that if we are giving the bounded input, whether we are getting the bounded output or not, and accordingly we get this thing. Okay. So, Bibo stability, you should remember this criteria. Then feedback systems, any system which takes um, consideration of the past outputs or past outputs, then to calculate the present output, then such systems, they are regarded as feedback system. Okay. So any of the inverting amplifier or the non-inverting amplifier, op-amp based inverting or the non-inverting amplifier, they are feedback system, because if you see in the feedback loop, we are having this resistance, this R2 resistance. Okay. So this is a feedback system. So any system which is taking the present or the past outputs to calculate the present output, these systems, they are regarded as the feedback system. With this, we complete this first preliminary chapter, signals and systems.